The first machine many American pilots learned to trust is not new. Its architecture matured before the jet age. More than 2,100 Lycoming-powered PT-13s served America's wartime training system. But that larger system produced 435,165 pilots, and Lycoming did not build it alone. So how does an engine stop being a product, and become infrastructure? Picture a student alone in a trainer for the first time. The instructor is on the ground. The runway is getting shorter. Every vibration now means something. The machine does not need glamour. It needs predictable responses the student has learned to read. In the early 1940s, America had to reproduce that first solo at national scale. One machine inside that effort was the Stearman Cadet. The Army Air Corps adopted it in 1936. Lycoming-powered aircraft were designated PT-13s. Continental-powered aircraft became PT-17s. Jacobs-powered aircraft became PT-18s. The distinction matters, this was never one company's story. More than 10,000 cadets were ordered for the United States and its allies. More than 2,100 PT-13s served the U.S. Army Air Forces with Lycoming's 220 horsepower, or 680. In those open cockpits, students learn takeoffs, stalls, landings, and fear without an instructor on the controls. But aircraft alone could not produce pilots quickly enough. In 1939, the Army had 4,502 pilots and trained 982 more. Output then accelerated, about 8,000 in 1940, and more than 27,000 in 1941. Metal was being manufactured. So was human skill. A nation can manufacture aluminum faster than it can manufacture judgment. America was turning flight into a repeatable process. The civilian pilot training program supplied the larger answer. It began in 1938 with a goal of training 20,000 civilian pilots a year. Colleges, flight schools, local airfields, instructors, mechanics, and many aircraft and engine makers became one mobilized network. The CPTP and its wartime successor produced 435,165 pilots for the war effort. The machinery of that program was institutional as much as mechanical. A college could provide classrooms and candidates. A local field could provide flying weather, runways, and daily repetition. Civilian instructors could expand a pool that military schools alone could not create quickly enough. Mechanics and suppliers kept the aircraft moving while government standards tied separate schools to a national purpose. The result was not one giant academy. It was a distributed production line for skill, assembled from organizations that already existed in American communities. That number is the first trap. Placing all 435,165 pilots behind a Lycoming engine would be dramatic, and false. The program used many institutions, aircraft, and power plants. Lycoming's contribution was real, more than 2,100 PT-13s inside a cadet family that trained many thousands. But the national advantage came from the connections. Lycoming did not create the system. It became valuable because the system could repeat what its engines made possible. Primary training was not the glamorous end of military aviation. It was the filter at the beginning. Before a student could navigate, fly formation, or handle a combat aircraft, someone had to teach the physical grammar of flight, attitude, airspeed, coordination, recovery, and judgment. The trainer therefore carried a strange burden. It had to be simple enough to teach in, demanding enough to expose mistakes, and supportable enough to repeat the lesson with the next student. That is why the first solo matters to this story. It is the point where industrial output becomes human capability. Its reach was wider than the military pipeline usually pictured on screen. The Air Force history records around 2,000 black pilot graduates and about 2,500 women trained by mid-1941. Those figures do not erase the barriers of the period. They show how civilian institutions expanded the pool of people able to enter American aviation. So why did this manufacturer become one of the standards the system kept? Lycoming had already changed identities several times. Before that moment, Smithsonian traces the company to a 19th-century sewing machine manufacturer. In 1907, it was reorganized as the Lycoming Foundry and Machine Company and produced automobile engines. It later became part of Auburn. The sequence matters because it shows industrial capability moving across products, precision metalwork, casting, machining, assembly, and engine production were not born inside aviation. They were redirected into it. That does not make the move inevitable. It shows why a company with no original destiny in flight could become useful when aviation demanded manufacturers able to learn quickly. Its early aircraft engines were radials, the arrangement visible on the PT-13s are 680. Then the company made another change. In 1938, it entered the light aircraft field with a horizontally opposed engine. The shift from a large exposed radial to a compact flat engine was not merely a new model number. It was a change in the kind of aircraft and mission the company could serve, from a prominent round power plant on a wartime trainer to an engine that could disappear inside the narrow cowling of a personal airplane. The answer did not begin with the engine people picture today. In 1938, Lycoming entered the light aircraft field with the O-145, 4 cylinders, air-cooled, and horizontally opposed. The 1939 O-145 B2 displaced 145 cubic inches, produced 65 horsepower at 2,550 revolutions per minute, and weighed 166 pounds. Those figures sound modest. Their importance was geometric. The engine was low enough for a pilot to see over, compact enough for a small nose, and simple enough to avoid the pumps, radiator, and coolant plumbing of a liquid-cooled installation. Air cooling created its own thermal demands. But for a light airplane, every removed system saved weight and complexity. The O-145 also arrived when the Piper Cub was making personal flight imaginable at a price below $2,000. But precision matters here too. Lycoming was one of several basic engine suppliers for the Cub, alongside Continental and Franklin. Not every Cub carried a Lycoming. The larger achievement was compatibility, a modest aircraft, a modest engine, local instruction, and an operating model that could spread beyond military bases. America's flying infrastructure did not grow from the most advanced machine available. It grew from machines that schools, owners, and mechanics could repeatedly put back into service. Fly. Inspect. Refuel. Repair. Fly again. That ordinary cycle is where a machine begins becoming infrastructure. The O-145 B2 appeared in more than one small airframe. Smithsonian identifies the Piper J3L-65, Taylorcraft BL-12-65, and Mooney M-18 might among its applications. That variety is more revealing than any one famous airplane. An engine family becomes a standard when designers can build different aircraft around it, mechanics encounter it in more than one context, and the knowledge developed in one hangar remains useful in another. The pattern was still small in 1939. But it established the logic that later Lycoming families would expand. The wartime emergency eventually ended. The need to create pilots did not. America no longer required one crash program on the scale of CPTP and WTS, but it still needed a continuous ladder: student, instructor, local aircraft, mechanic, examiner, and the next level of training. Much of that work lived far from airline terminals. It happened at general aviation airports and flight schools where the same aircraft might serve several lessons in one day. The national pilot pipeline became less visible than wartime mobilization because it was no longer one named program. It became routine. That transition was not automatic. On May 13, 1946, President Truman signed the Federal Airport Act. FAA describes it as the first peacetime program of federal financial aid devoted exclusively to developing the nation's civil airports. The timing is important. Barely 8 months after the war ended, the federal government was converting aviation from an emergency military capacity into a permanent civil project. Runways and airport land were becoming part of national planning, not just local ambition or leftover wartime geography. The scale of the commitment was substantial for its time. The act authorized $500 million for the contiguous United States and another $20 million for Alaska and Hawaii over 7 years. Federal allotments were to be matched by local funds. That matching structure forced 2 levels of government to participate in the same physical network. Washington could help finance an airport, but a community also had to decide that the runway belonged in its future. Infrastructure grew through coordination again, this time between national money and local commitment. The first construction program in 1947 listed 800 airports for construction or improvement. The first national airport plan forecast requirements involving 4,431 locations. These were plans, not proof that every airport was completed exactly as imagined. But the numbers reveal the scale of the question officials were asking. The country was not planning only a handful of glamorous terminals. It was trying to understand where thousands of civil aviation facilities might be needed. The administrative system was decentralizing too. In June 1946, CAA regional offices became the approving authorities for flying schools, repair stations, ground schools, mechanic schools, and parachute lofts. FAA's chronology says the change was driven by a growing number of applications. That is an unusually direct glimpse of a system becoming permanent: more schools, more repair organizations, more certificates, and too much activity to manage only from Washington. The post-war pilot ladder required local institutions, but it also required a repeatable way to recognize and supervise them. That is where scale mattered. NASA's typical aircraft study records 36,503 O-320 engines and 15,858 O-360s in its production table. Those figures are not current market share claims, and they do not mean every trainer used a Lycoming. They show that the engine families existed in numbers large enough for parts, manuals, overhaul practices, tools, and maintenance experience to accumulate around them. A flight school choosing an aircraft was therefore choosing more than horsepower. It was also choosing whether a nearby shop could inspect it, whether parts could be found, and whether instructors already understood the machine's operating language. The training ladder depends on ordinary repetition. A student flies a lesson. A discrepancy is written down. A mechanic interprets it, inspects the aircraft, and returns it to service. An instructor trusts the process enough to put the next student aboard. None of this makes the engine infallible. It makes the work transferable. Knowledge can pass from one mechanic to another, one school to another, and one generation of pilots to the next. Lycoming did not run the schools or own the airports. Its importance came from becoming one of the mechanical standards that many independent organizations could coordinate around. An engine still cannot become infrastructure without places to use it. The Federal Aviation Administration describes nearly 3,000 general aviation airports, heliports, and seaplane bases in the national plan as a national asset. About 88% of airports in that plan are general aviation airports. On a map, many look insignificant: one runway, a fuel pump, a hangar, perhaps a small school. Together, they form a distributed layer beneath the airline system, the places where aircraft can be based, inspected, repaired, and flown without beginning at a major terminal. The federal commitment did not end with the first post-war program. In its 2022 account marking 75 years of airport grants, FAA reported $96 billion distributed for 82,308 airport projects through the original Federal Aid Airport Program, the program that followed in 1970, and the Airport Improvement Program established in 1982. Those are dated cumulative figures, not a claim about spending in 2026. They show that the airport map was maintained through decades of repeated projects rather than created in one burst after the war. This is a different map of American aviation. The famous airports are bright hubs. The general aviation network is connective tissue, smaller, quieter, and spread across the territory. Its value appears when a community needs a training flight, an emergency aircraft, a business trip, or simply a usable route into the national system. FAA says basic airports connect communities to the national airport system and support emergency response, air ambulance, flight training, and personal flying. Lycoming does not own those functions, and its engines do not power every aircraft performing them. The relationship is more practical. Familiar piston fleets give many local operators equipment that existing mechanics, instructors, and parts channels already understand. A training aircraft can fly a lesson in the morning, enter maintenance in the afternoon, and return through a process the local system has rehearsed many times. Repeatability, not corporate mythology, is the source of capacity. That capacity matters because aviation skill is perishable. Pilots need hours. Instructors need students. Mechanics need real machines on which to build judgment. Airports need activity to justify fuel, hangars, lighting, and maintenance. None of these elements creates the others alone. But when they coexist, a small runway becomes more than pavement. It becomes a place where national aviation knowledge is reproduced one inspection, one lesson, and one first solo at a time. Lycoming became important in this geography because familiar engine families could travel through it. The claim is not that every future airline pilot begins behind a Lycoming. The claim is that distributed general aviation helps create the people and practices on which the larger system depends. The distributed system had a weakness: it still depended on an aircraft market able to renew the fleet. In 1978, U.S. manufacturers shipped 17,811 general aviation airplanes. By 1994, the number was 928. That is roughly 19 lost annual deliveries for every one that remained. No single cause explains the collapse. Liability pressure mattered, but so did demand, financing, the economy, regulation, and the rising cost of new aircraft. For this story, the important consequence is not simply that an old engine survived. It is that schools, owners, mechanics, and airports had to keep extracting useful flying from the aircraft already available. A smaller market made clean sheet replacement harder to finance, while the installed fleet became a bridge between one generation of pilots and the next. Overhaul knowledge, parts channels, and familiar procedures gained value because the training system could not pause while the industry waited for a perfect successor. That is an editorial synthesis, not a claim that every school made the same decision. Congress changed one pressure in 1994 through the General Aviation Revitalization Act. The law established an 18-year limitation period for certain civil actions involving covered general aviation aircraft and components, within a defined scope and with exceptions. GAO later found that most general aviation indicators had declined before GARA and reversed afterward, sharply in manufacturing and less strongly in flying activity. The evidence supports a liability mechanism. It does not support saying that one law revived the entire system, or froze engine design in time. The pressure now includes people as well as aircraft. GAO reported in 2023 that enrollment in U.S. pilot training schools had increased and that airlines were creating flight schools. Yet it remained uncertain whether future pilot supply would meet demand. GAO also found that the number of newly certificated mechanics rose from 2017 through 2022, while aviation businesses still reported difficulty maintaining sufficient mechanic staffing. More students do not automatically create more flight capacity if aircraft wait for maintenance or if schools cannot retain enough instructors and examiners. The newer evidence is equally complicated. GAO reported in 2026 that pilot certifications grew about 10% from 2017 through 2024, with most of that growth after 2021. At the same time, selected stakeholders connected regional pilot departures with reductions in service to small communities. One network airline told GAO that it withdrew regional service from 29 airports in 2022. These are not Lycoming outcomes. They show that producing pilots, retaining them, maintaining aircraft, and preserving local service remain different parts of the same capacity problem. Return to the first solo. The student sees one airplane, one runway, and one engine. Behind that moment is a much larger structure, an instructor certified to teach, a mechanic authorized to sign the aircraft back into service, parts and manuals that can reach a local field, an airport that remains open, and an accumulated language for describing what the machine is doing. The engine matters because all of those people can act around it. That is the real distinction between a product and infrastructure. A product is purchased. Infrastructure coordinates people who may never work for the same organization. Wartime schools coordinated around trainers and procedures. Post-war flight schools coordinated around local aircraft, instructors, maintenance, and examinations. Airport operators coordinated fuel, hangars, lighting, emergency access, and runways. Lycoming did not command that network. Its engine families became one durable mechanical interface inside it. This is also why the company's legacy should not be reduced to an engine that refused to die. The more important achievement was continuity of capability. A pilot trained in one place could recognize familiar behavior in another. A mechanic's knowledge could remain useful beyond one airframe. A school could draw from established parts and overhaul channels. None of those advantages is universal, and none proves that Lycoming was always the cheapest, safest, or best choice. Together, they explain how a mechanical standard can lower the friction of keeping a distributed training system alive. The system now faces a different test. In 2024, average daily departures per route at non-hub airports were 19% below 2018. More than 70% of non-hub airports without essential air service support saw declines. Those are airline service figures, not Lycoming figures, but they reveal the pressure on local access. Training pipelines also need usable aircraft, instructors, mechanics, and airports. Preserving an old engine is not enough if the surrounding capability weakens. New propulsion will have to improve efficiency and emissions. It may use different fuels, different controls, or a different architecture. But technical progress becomes national capability only when schools can teach it, mechanics can support it, regulators can approve it, and local operators can afford to use it. The next American aviation standard may not look like a Lycoming. It will still have to solve the coordination problem that Lycoming's installed families helped solve. That future standard will also need a path for transition. A new engine can enter one aircraft while thousands of existing trainers remain in service. A new fuel can become available at one airport while another field still depends on the old supply chain. Electric or hybrid propulsion may change maintenance and energy infrastructure as much as it changes the aircraft. The challenge is not choosing between preservation and invention. It is creating enough overlap that training and local access continue while the system learns something new. So what happened to Lycoming? It did not build American aviation alone. It became one of the repeatable mechanical standards inside the system that produced pilots, sustained local flying, and carried aviation knowledge across generations. The machinery helped make America strong not because it was magical, but because thousands of independent people and places could organize useful work around it. That coordination is the deeper legacy. It is also the next American design challenge. Ordinary is what successful infrastructure eventually looks like. Inventing the machine is only the beginning. The harder achievement is building a world that knows how to use it. If there is another overlooked machine inside America's infrastructure that deserves this kind of audit, name it below.